Hello everyone, in this presentation we will discuss about observer-based impulsive controller design for hepatitis C infection under delayed and sampled measurements. Hepatitis C is an infectious disease of the liver that is caused by hepatitis C virus which transfers through the blood streams. This disease affects an estimated of 170 million people globally and is the main reason of liver cancer, cirrhosis, and deaths of many people globally. Unfortunately, there is no effective vaccination for the disease, and therefore antiviral drugs are utilized for the treatment of the infection. Combination therapy, which consists of weekly pegylated interferons injection and daily consumption of ribavirin, and also using direct-acting antivirals, are the current treatment methods of HCV infection. Due to the unavailability of the vaccination and also progress of the infection to other dangerous diseases like cirrhosis, cancer, and finally death, many researches have been carried out for proposing an effective treatment strategy by using control theories. For proposing such a scheme, the practical and intrinsic features of the nonlinear system should be considered in the design. For example, pharmacokinetics and pharmacodynamics equations of the drugs should be considered with the mathematical model of the disease in order to have a relationship between the drug dose and its efficacy. Also, the impulsive nature of the drug input should be considered in the controller design. When the drugs are administered, the system states changes impulsively and it makes the system impulsive. Therefore, the impulsive nature of the drug input should be considered in the design. Also, another factor of the HCV treatment is the drug dose limitation due to its potential negative side effects, and this factor should be handled in the controller design. Another practical feature of the HCV treatment is unavailability of all system states due to the high cost of measuring devices. In the HCV treatment, only the viral load is measured in order to investigate the patient's response to antiviral therapy, while for the controller implementation, we need the system states. Therefore, they should be estimated by using a nonlinear observer. On the other hand, the viral load measurements are only available at some certain impulse time and not the whole time intervals. And it takes a time to obtain the result. In other words, the measurements are subject to delay. Therefore, the observer should work under the delayed and sampled measurements. The purpose of this study is proposing an observer-based controller for the treatment of HCV infection with pegylated interferon alpha-2b under impulsive and limited drug input and also delayed and sampled outputs. In other words, we have considered all the mentioned features of HCV treatment in the controller design. In order to propose such a scheme, an appropriate mathematical model should be considered. Newman proposed the basic model of HCV infection in the body. This model consists of three variables. T shows the healthy cells concentration, I infected cells concentration, V viral load, and epsilon drug efficacy. As it's clear from these equations, the healthy cells are produced by constant rate S and their number decreases by constant rate D. Also, they are infected by the constant rate beta. The produced infected cells die by constant rate delta and they produce virus particles by rate P. On the other hand, the produced virus particles declines because of the natural death by rate C, and also using the antiviral drugs decreases the production of the viral load from the infected cells by the factor epsilon, which is the drug efficacy. In order to have a relationship between the drug dose and its efficacy, we use the pharmacodynamics and pharmacokinetics equation. The pharmacodynamics of the pegylated interferon is based on the Hill equation, and in this formula, C2 represents drug concentration in blood, and EC15 is the drug concentration producing 50% of maximum efficacy. Also, in order to have a relationship between the drug dose and the concentration of the drug in the blood, The pharmacokinetics equations have been considered. In this equation, C1 is the concentration of the drug in the absorption site, tau k is the weekly drug injection time, D is the drug dose, F drug bioavailability, VD drug distribution volume, and Ka and Ke are the absorption and elimination rates. As it's clear from the second equation, the concentration of the drug in the blood changes impulsively after the drug administration. By considering pharmacodynamics and pharmacokinetics equation, as well as the Newman model, this new extended model has been obtained. In order to move the uninfected equilibrium point of this extended model to the origin, this new variable has been defined, and the model equations becomes as this formula. In this equation, x is the vector of the states, b is a constant vector, and f is the vector of nonlinear functions of the model. Also, nu is the control input, that is the drug dose, and x plus shows the states value after the drug administration. In order to consider the drug dose limitation, the input saturation nonlinearity has been considered. And in this equation, nu is the drug dose that has been defined before, and u is the saturated control input. Also, nu max and nu min are the values that are available in the literature. By considering this relationship, the system model becomes as this equation. The control objective is reducing the viral load to the cure boundary, which is one virus in the total body plasma. In order to reach that objective, an impulsive state feedback controller has been designed at each impulse time, and L is the feedback gain. Since there is a delay in the measurements of the viral load, therefore, the control input becomes as this equation. In this equation, delta is the measurement delay. On the other hand, because of the unavailability of all system states and that the viral load measurements are only available at certain impulse times, we should use the estimation of the states for finding the control input. In order to estimate the unknown states of the system, an observer should be designed under delayed and sampled measurements. The dynamics of the observer is composed of two parts, the continuous time part and the impulsive part. The continuous time part of the observer acts as open loop estimator, since we don't have any information of the output between the injections, and the impulsive part acts as closed loop estimator. In order to design the observer, we have considered some assumptions. The first one is that the drug injection is carried out weekly. The second one is that the viral load measurements are carried out before each injection. And the last one is that the measurement delay is 7 days. It should be noted that these values are based on the clinical application, and any other value can be considered for the observer design. The observer dynamics is divided into two parts. The first part is the estimation of the delayed state, or the estimation of the state at time t minus delta. In this equation, x0 is the estimation of the state at time t minus delta, and u0 is the saturated control input at time t minus delta. Also, k1 is the observer gain. On the other hand, the estimation of the real state, or the estimation of the state at time t, is divided into two time intervals. For the times between 0 and 7 days, the observer acts as open loop estimator because we don't have any measurement at this time. And for the times more than 7 days, the observer acts as closed loop estimator. X hat is the estimation of the state at time t, K2 is the observer gain, and U is the saturated control input at time t. By considering some values for the model parameters and also controller and observer design parameters, the simulation has been carried out, and the results are shown here. This figure shows the time variations of the viral load, and as it's clear, the viral load decreased to its desired value or to the cure boundary, and the controller objective has been achieved. This figure shows the drug input of the corresponding controller, and this figure shows the time variations of the healthy cells by the blue line and its estimation by the dashed red line. This figure shows the infected cells and its estimation, the viral load and its estimation, the concentration of the drug at absorption site and its estimation, the concentration of the drug at blood and its estimation, and all of these figures shows that the observer has a good performance and the estimated states converge to their actual values while the controller objective has been achieved. Also, in order to check the closed-loop performance under other model parameters, the Monte Carlo simulation method has been utilized, and the model parameters have been varied with uniform random distribution within the interval 40%. This figure shows the viral load variations for one set of the generated parameters, and it's clear that again the control objective has been achieved and the viral load decreased to its desired value. And finally, this figure shows the corresponding drug input of the controller. Thank you very much for your time and for your attention.